All right, hi, welcome everybody to our panel To the Extreme. I'm Dr. Caitlin Ahrens out of NASA Goddard Space Flight Center, and I am joined by...
I'm Dr. Brian Gray. I am a professor of biology up at York College of Pennsylvania, about an hour north of Baltimore. And I am a microbiologist by training to complement in a totally weird and normal fashion, Dr. Ahrens, who is...
Yep, I am a planetary geologist and an astrophysicist. So when Balticon started their programming, they pretty much teamed us both together. We had never known each other before, anything with Balticon before. And so we're like, oh, what could possibly go wrong between an astronomer and a microbiologist? So we've actually had several conversations before Balticon, and so we hope that you enjoy our bantering of what's been going on actually with what is extremophiles. So let's go ahead and start off with that.
Fair enough. So extremophiles covers organisms that live literally at extremes. And so that means literally any characteristic you can think of. Temperature, both high and low, salt concentration, radiation, what are the weird ones? Water availability, that's a challenge, as well as pH. My brain is now going, you haven't taught this in like 6 months. You don't remember anything. So, and an interesting one that I came across recently is metabolic extremes. I was just reading an article this morning about organisms living off of hydrogen, of all things. So, yeah, it's a lot of fun. That's the part about microbiology that I love so much. My personal training, just for the record, is that I came at this from medical microbiology, from disease processes, and yet microbiology is such a wide, broad area that extremophiles and the interface with exobiology, xenobiology, is really easy to make.
That is interesting. So coming at it from a planetary perspective, we always point at planets and go, could life either originate at a certain place, or what if we accidentally contaminated? And you can have cross-contamination. We have that as an issue. That's a whole branch under NASA called the Planetary Protection Program.
And
so
I
we
love
have to
the
be
fact
careful.
that NASA has been thinking about that for long enough that they have the Office of Planetary Protection, which, you know, you might think movies like Armageddon and Deep Impact come out of, but no, that's not what it means. It means that life, we get everywhere.
Well, and then can we accidentally bring life to a certain habitat where if there was already life, could we accidentally destroy life already there? Or could we bring life to, say, Mars, and it just completely overtakes the whole planet? So it's an interesting cross-contamination problem that we need to be very careful of. And don't sneeze on the moon rocks.
Bad idea.
Yeah.
Yes. Actually, the article I was reading this morning, I came across, it was talking about a researcher who had started out in the Canadian Shield. So here's something that might kind of interest you. And one of the things that I did not know, so I'll rely on you to confirm this one, Caitlin, is apparently the Canadian Shield, the continental shield in there, is isolated from other groundwater supplies. It's not a continuous aquifer. And so it's got this separate deep pool of geologic water that goes down a few kilometers.
That is so cool.
Yeah,
that's really cool. We're actually using that as an analog to Mars currently, because we're realizing that Mars also has very isolated subsurface islands of whether there used to be water or there is current water, not fresh, take a dive kind of water, but very briny,
right.
very salty
yes,
water.
Extreme salinity.
Mm-hmm.
Yeah. And I mean, so I'm aware of that for things like salt marshes and so on. But apparently this research group, who is out of North Carolina State and New Mexico State University, they are looking at microbes in the Canadian Shield there and finding that radiolysis, so radioactive breakdown of water to produce elemental hydrogen and elemental oxygen, is sufficient to maintain life, which I found was absolutely, I'm kind of like, oh, okay. So we literally have microbes making use of all different kinds of radiation. You know, I've mentioned to you last time we talked about the microbes that use the gamma irradiation inside the Chernobyl reactor, and the recent discovery of microbes photosynthesizing from infrared radiation down at the geothermal vents. And so they're making direct use of radiation, but now we have microbes using the byproducts of radiation, which I find, you know, as an utterly fascinating kind of, here's the entire set. Have microbes that collect all the photons and then the radioactive particles kind of thing.
No, and radiation is such a huge ordeal as far as like astronauts go, and certainly the future of our human exploration on like the moon and Mars. But it's so interesting that there's bacteria that would thrive on this radiation. And there's the cool part is that every planet has its own deal of radiation.
Mhm.
You have Venus as its own separate radiation heck hole there, but also the ocean worlds, Europa and Enceladus, and Titan. They certainly have their own radiolysis type processes going on, whether in their oceans and their atmospheres. It's just so fascinating.
There, at least for Titan and Enceladus, we're talking about both tectonic flexing because of gravitational pull, as well as electromagnetic heating. Is that, if I'm remembering rightly?
That's more so for Europa. Enceladus okay. is a slightly different moon ocean entity where you have a little bit of tidal flexing, but it may have more like hydrothermal venting is
okay. So that one's kind of much more terrestrial in our current model, I'm assuming, in terms of how it heats in many ways.
Yeah. Now, what actually powers the hydrothermal heating, at least with Enceladus, we're like, there's guesses. But the problem here is that we don't know how thick the ice sheet is. That's our main oops. We don't know. So right. there's like, you know, you can only do so much math and go like, it's this thick to this thick. The math is gonna work out one way or another.
Until we actually land a drill on there to find out. Yeah.
Right. So Europa is at least gonna have a mission by 2027, I believe. It's a Europa Clipper, and so that's gonna it's gonna be an interesting mission to say the least. It's going to be an orbiter, but there may be a small lander with it, with like an 80-meter drill. And
are they still designing it then?
Yeah, the instruments have at least been semi-confirmed, at least for the orbiter. But right. Yeah, they're still trying to lay it out.
It doesn't have 7 minutes of terror to deal with, so.
Well, no, it has like several years worth of terror because it needs to get there. It's going to take about 5 years to get
right.
there.
I was thinking of the famous bit about 7 minutes of terror to get down to the surface of Mars.
Oh, I've been there. I have actually been in a control room for the Phoenix Mars lander. I was in a control room for the Green Bank telescope to receive the first signal for Phoenix.
Nice.
And you can feel the electricity of just that 7 minutes of terror of, did it land okay?
I believe that. I can totally believe that. Yes.
But speaking of Phoenix, though, that was kind of our first dive into trying to confirm water on Mars.
Right. And what we're finding, at least here on Earth, is that we can get away with very, very little water indeed. One of my favorite, I don't know if I ever actually want to visit there, but the Namibian desert, which is sub-Saharan, and it's the bottom edge. I believe it's part of the Sahel, and it on average receives less than 2 centimeters of rain a year. And it's all in pretty much one season. And so this was one of those places that scientists originally said, okay, we need, at least for terrestrial life, we need water. And if there's gonna be one place on Earth that's not gonna have any significant water, it'll be here, right? Yeah, no, they dug down, and literally 1.5 inches beneath the surface, they found microbial mats growing in the soil. And so it's yeah, exactly. It was one of those things that I'm sitting here going like, all right, let's see, what can we rule out? How dry can it get? You know, come here, science literature. And we asked, so, you know, it's as long as it avoids the temperature swings of the day, apparently life there is pretty happy and pretty stable. So
that's interesting. Okay, so now we have to keep in mind of just the temperature swings.
Yep.
Which is, it's very easy on subsurface levels though, but on Mars, now there's temperature swings, or Mercury, there would be temperature swings.
I can imagine.
There are cloud layers of Venus that have a nice, steady, constant, temperate temperature, thankfully, which is nice.
Right, and given that we have found, again, terrestrial life, we found in our atmosphere, we certainly don't need a solid substrate, and it looks like dust particles are sufficient for a solid substrate for some organisms to actually have a physical footing for life. But we found many microbes that don't need any solid contact at all. They can grow entirely in liquid suspension, never touching a solid surface. So, you know, all of those options are exciting and different and weird to think about. So
that's, oh my goodness.
Yeah, no, the fact that we've recovered, so the problem is when you're doing sampling at 500 miles an hour, you don't necessarily preserve three-dimensional structure of what you're sucking into the scoop, but we have found living bacteria, let's see, 7 miles up, I think is the record so far. Actually, that we find evidence of, if we look at metabolic processes, we find evidence of them living, growing actively 7 miles up, which I'm not much of an atmospheric scientist, but the average temperature there is something like it's -20 centigrade. It's very cold. But there's enough moisture up there, and there's all the solar radiation you might want, kind of thing. So yeah, it's yeah, we can push things. Microbes love, yeah, they kind of like, so they're for a few years in class, I taught a general microbiology course. My main teaching is medical microbiology, but I taught a general microbiology course, and I had a saying that I would drop in class of, life finds a way where there is energy. And as long as we can identify that energy, apparently microbes will use it. So, I mean, honestly, the fact that we have discovered Deinococcus radiodurans, which lives inside of reactor cores, and grows in the presence of 5 grays of radiation. No relationship whatsoever, but that is a level of radiation sufficient to kill a human being in less than a minute. Yeah, exactly.
Ooh, okay. Ooh.
Yeah, you know, it's a crazy level of radiation, and the fact that we have microbes that live there, and they have very interesting lifestyle in the terms of what we normally consider for a bacteria. So yeah, so it's a lot of fun to think about. And as we find more, it's great to think about, well, okay, what are our limits?
For sure. And this, honestly, and obviously it opens up a whole no pun intended, can of worms for planetary scientists, though, because we're now in the age of planetary science where we're starting to build laboratories. There's a couple laboratories through the nation, and now with international partners, where we can simulate different planetary surfaces. And so most Mars simulation chambers, which I kid you not, it looks like something out of very steampunky looking machines. Awesome. They're very, very shiny, the big bolts kind of deal with the big vault door. You put the sample inside, shut the door, lock it, and then it goes down into the temperatures and pressures of Martian conditions. And it looks so surreal to see some of these chambers. Some of them, you will never open it. You would just have these little test tubes, and you would syringe, like little mechanical arms would just syringe in the liquids or the different salts. And then we have methanogens is the bacteria that we would want to figure out. You want to explain a little bit about what methanogens are?
So methanogens are a fascinating group, and as you might guess from the name, they make methane. That's actually their waste product. They are a category of life that we call autotrophs. And so many methanogens can metabolize carbon dioxide, and they will break carbon dioxide down for those high energy oxygen bonds, carbon oxygen bonds, and they will stick methane on, they'll stick hydrogen groups on them. And so their waste product is methane. And that was, I remember when the first data that came back suggesting there were methane plumes, or at least methane puffs, in the Martian atmosphere, the extremophile microbiology crowd kind of went, whoa, what's going on? And that was really kind of interesting to watch in many ways. And so, yeah, we have terrestrial methanogens. Very commonly, we find them living at the bottom of marshes, oddly enough. One of the best known groups of methanogens is actually, if you go out to the Woods Hole laboratory at the end of Cape Cod, they've got a marsh off the end there that there's actually a common photo in many microbiology textbooks of one of the instructors from Woods Hole of going out there with a funnel and a lighter. And what they would do is basically they would stick the funnel on the top of the water, and they would have the students who you're walking around with like a classic adventurer's 10-foot pole, so you don't trip and fall over. And they're kind of like, all right, somebody come over and stir up the mud underneath my funnel. And the students would kind of like, yeah, sure, whatever. We're gonna have, the flame swamp, yeah, whatever. And he would stand there with the funnel, and as the students started stirring up the mud, they'd flick, 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 and they would have a gout of flame, and they would have a methane flame burning from the funnel. And then he would kind of move it over, and somebody else would come over and make the flame swamp. And so that's basically disturbing the methanogens and getting them to the trapped gas bubbles to release right there. And so
you're essentially scaring them to burp and fart real quickly. All that methane, you're scaring them.
Yeah, absolutely. And so it's the hypothesis for a long time was that they required a significant amount of water. But I've known a few folks who do methanogen research, and they can get by with a limited amount of water. They can function at a variety of temperatures. The two requirements they have for growth are, one, no oxygen. Oxygen is poisonous. Oxygen is chemically speaking one of the worst poisons on the planet. And two, a source of carbon dioxide to break down the carbon dioxide to stick hydrogen groups on it. So. Yeah.
And that's perfect with Mars, because there's definitely a bunch of methane. The atmosphere is methane. And then most of the ice on Mars is carbon dioxide ice.
There you go.
That's perfect.
So lots of growing material. And then the other one, which we were talking about last time we chatted, was the phosphine signatures in the air of Venus.
Yes, when that news report came out, I believe this was like nearing the end of 2020. It was hysterical because this phosphine signature popped up in telescopic data, mostly using Arecibo and also a number of other telescopes kind of deal. And this detection popped up, immediately went into to publish a paper, and it just blew up the planetary community because it was like, oh my goodness, this is like building block of life chemistry on Venus. But then there was like this huge debate with the planetary community of like, wait a moment, hang on, are you sure you actually saw this detection? Because you're looking at a signal that's like this big in data that's like this big. Kind of deal, are you sure it wasn't just noise? Is it like that weak of a signal that it could have just been like the methane plumes of
Right.
Mars? It's like
Exactly.
we've never seen one again. Could it have just been a volcanic fluke? Yeah.
Right.
Or definitely a data fluke or something like that. But there's still the debate of like, nope, we found it. No, we didn't. We found it again. Maybe.
do we trust our readings?
So we're at the maybe stage again. Yeah, it's going to get interesting, to say the least.
And so for those of you unfamiliar with phosphine, it's a small carbon and hydrogen molecule that many organisms actually produce transiently for a very, very brief period of time. And it is a component of cell membranes. Actually, many, many microbes that use it, actually our cells, we use a different pathway to make our membranes, but all living cells that we know of are wrapped up basically in envelopes of lipid, of little fat that makes these little bubbles, which we recognize as cells. And so there are certain categories of microbes that use phosphine as a building block. They will create phosphine and then patch it together to make their membranes to hold the cells together. And so, I remember hearing about the phosphine signature and going like, oh, this is a sign of life on Venus, and kind of like, it's too small of a hydrocarbon to be 100% certain. If they were talking about a branched hydrocarbon, I'd be losing my mind. But it's a little tiny thing. So
it's a little tiny hydrocarbon. But it kind of brings up the whole discussion in the planetary community of like, you know what, there's a lot of hydrocarbons in space, and we're just now realizing like how to detect them, because they are actually very extremely difficult to detect with telescopes and also spectrometers and so on and so forth. But to determine like how they're formed is still something of interest. So whether it is on Venus, is it a hydrocarbon of just a chemical compound, or is it actually from something? Is still something
given the environmental extremes of temperature and pressure that we have observed even briefly on Venus before our equipment melted, Venera probe, that
several.
The entire possibility of abiotic, meaning non-biological formation of those chemicals is something we need to consider first, honestly. And it's really easy to get very, very excited and say, ooh, there's this thing. But it turns out that we should be considering the abiotic processes first. So
yeah, absolutely. And that's pretty much where us geologists come in and go like, well, okay, could there be like a volcanic source for some of these hydrocarbons? Or Venus is weird because you have volcanic systems, you can have rift systems where subsurface gases could also geyser up as well. There's some really weird storm systems that we're still trying to figure out with the Venus. Venus is just weird. Now, early next month, we're supposed to find out whether NASA is going to approve a Venus mission So that's going to be exciting if we actually get a Venus mission, because if anything, that will be the very first Venus mission out of the United States. So yeah, that could be something interesting for us. So currently there's actually 4 missions in the running right now. There's 2 for Venus, 1 for Io, which we'll chat about here, and then the other one is for Triton, around Neptune. So that drum roll everybody kind of deal, because trust me, us NASA people are all just kind of at the edge of our seats waiting for like, which mission is NASA going to choose? So it's gonna be interesting though. But Io, oh my goodness, you want to talk about some really weird extremes.
Yes.
Io, you have sulfur dioxide. Oof.
Yeah, and which from a chemistry perspective is utterly terrifying, because it's the precursor to sulfuric acid. You add water to sulfur dioxide and you get one of the most corrosive chemicals that we have so far figured out.
Yep. So basically the entire moon of Io, one of the smaller Galilean moons around Jupiter, if you were to Google an image of Io, it just looks disgustingly yellow and goopy and
it's
very,
kind of
very volcanic.
The classic mental image of a planetary inferno. It's got volcanoes, it's got plumes erupting into space. Yes.
Yes, and it looks like molded cheese on the side. So yeah. For something so cool, it just looks so awful.
Yeah,
but you know what?
We have found organisms that both process and produce sulfur dioxide. Yeah.
See, there we go.
There's a lot of those are extremophiles. They live at the boundaries. So the ones that excuse me, I'm thinking of at the moment that produce sulfur dioxide are down at the geothermal vents at the bottoms of Gulf of Mexico and similar places. But the ones that can process sulfur dioxide and use it as an energy source, we can find those in a variety of places, in a variety of more normal environments that I recall. So
yeah. What is normal? What's considered normal in the world of a microbiologist with extremophiles?
Right. And so as a comment, as a momentary aside, I'm seeing some questions pop up in the Q&A. We'll start answering those in a few bits, but somebody actually in there mentions the term Goldilocks. So humans, to take that as a jumping off point, humans, we are so self-centered. Everything has to be about us, and we like considering our living conditions, of course, the only ones that can support life, because for, 400 years, that's really all we could pick up on was our conditions. And so what is normal to a microbiologist? Ideally above the freezing point of water, below about I'd say on average 50 centigrade, so halfway to the boiling point of water, air pressure or atmospheric pressure around 14 pounds per square inch around 1 atmosphere, and some kind of energy and some kind of carbon source. That's really what's normal for microbiologists. And in fact, we find probably 70% of the species we know of microbes live within those parameters. So for those of you curious about the background, in my case, this is actually Yellowstone National Park. What you're looking at is Yellowstone Falls. And right before we started, Dr. Ahrens and I were talking about the microbiology found at Yellowstone, not to mention some of the cool geology found at Yellowstone, hitting up both of us. And one of the most interesting microbes found at Yellowstone is this particular one called Thermophilus aquaticus, nicknamed as TAQ, T-A-Q. And the only thing, so it prefers around 1 atmosphere, a little bit lower than 1 atmosphere of pressure. It lives in water. its carbon source, it happily feeds off of dissolved carbonate from rock that has been dissolved, limestone and so on that's been dissolved. And its ideal growing temperature is actually around 65 to 75 centigrade. So it lives in hot springs. And there is a great photo of, this was taken, I want to say, in the late 70s, or late 60s, I want to say, when they were kind of like, oh wait, maybe that color in that hot spring is biological. Let's go sample it. And there's this photo of a guy, he's wearing a polo shirt and khakis. He has a sampling pole that's probably 12, 15 feet long that has a glass beaker taped to the end of the sampling pole. And somebody is hanging onto his belt as he is leaning out over the edge of this hot spring with this pole trying to take a dip sample. And there's one other person behind the belt holder who's just kind of going like, and apparently everybody was fine. The guy brought his sampling pole back in, and that was apparently one of the samples taken for this organism, Thermophilus aquaticus. And we, being clever sapiens, hominids, we have turned that organism into a tool. If you have heard anything about the assay polymerase chain reaction, which, is currently used for a really popular and very common diagnostic test. In this, maybe some members of the audience have had a PCR test in the last, 14 months, that it's, yeah, no, I'm serious. The best test out there for COVID is in fact based off of an enzyme that we have purified from Thermophilus aquaticus. It's an enzyme we call TAC. But so, yeah, no, we take extremophiles, we take the weird things, and we go, what can we do with this? How can we use this? And so that actually came out of Yellowstone National Park. Of interesting. So
that is so cool, and I'm laughing at not only the beaker sampling story though, but we would still probably do that. We don't have very shiny brand new like technology kind of thing like that now. We probably still would have the pole and duct tape a beaker to the end of the pole.
Well,
we would probably still do that.
I was reading an interview earlier this week about a group of deep sea oceanographers who are doing sediment sampling. Now, apparently some part of the group was doing robotic sampling for mineral deposits, the classic manganese nodules, for example, which is its own sort of story. But the biologists in the group were kind of like, yeah, can we get down there in a manned submersible? And the engineers are kind of like, why? Robots are cool. And the biologists going like, yeah, no, we want to be able to sample from there and not there. And the engineers kind of like, okay, sure. And the biologists kind of like, no, we want to actually get down to the submarine and do the little Waldos and control the sampling, so we can be more precise about sampling. And so, yeah, no, the biologists, we're the ones who are kind of like, safety regulations? Nah.
Yeah.
Get us to where the cool, interesting stuff lives. Come on now, come on. Let's get into it.
Well, and then you pretty much described like why we want to bring people back to like the moon and then eventually Mars, is that, rovers are fine, landers are fantastic, but it then comes down to the human ingenuity side of things, where it's like we want to be able to see the landscape and see like, that looks like a cool rock. Take it.
Exactly.
Figure out like, oh, where can I drill? Where can I put this kind of instrument? Kind of deal. It's gonna get really interesting. There's a lot of lunar missions coming up. I know a lot of people are gearing up for the Artemis program. If you're not aware of what Artemis is, it's to essentially be Apollo program 2.0. So the Artemis 1 is actually supposed to launch end of this year, which is going to be cool. It is uncrewed though, so it is going to be lander rover. We're going to have a couple landers and rovers on the moon first, just to kind of scope out the area, scope out like our technological shininess and everything. But at least until 2023, 2024, and then onward to 2026, then we're going to start having crewed missions with Artemis 2 and Artemis 3. So we already have 3 missions planning currently right now.
They're on the books.
Yes,
That's
they are
exciting.
on the books. We are already figuring out like what instruments we're going to have with them. Now it's just a matter of where are we going to land them. So that's where
I
our
was going to
problem
ask
is right
that
now.
one next, and I'm assuming these are all planned on being short-term missions. Don't set up any sort of long-term facility. These are all.
Yes, at least landers and rovers can last longer. As long as there's enough sunlight, which is a little tricky to do.
Of energy.
Yes.
Yeah, and we're still using decaying radionuclides for thermoelectric power, right?
Somewhat.
Okay.
Somewhat. So we're still reliant on solar panels for some of the lunar missions, but yes, okay. Yes, radiogenic. Yes, as far as a lot of nuclear power, that's more for the Mars rovers. Okay. Yeah.
Cool. Yeah, so there's a lot of interesting stuff to look forward to as an exogeologist and a microbiologist with a passion for extremophiles. So
exactly. All right. So the one Q&A was talking about Goldilocks.
Right. So the more we learn about extremophiles, the wider the Goldilocks zone seems to get. Are there exoplanets we now consider as possible habitats for life of some sort that were ruled out as too hostile in the past?
Oh, goodness gracious. So the really cool part about exoplanetary systems is that at first, for a number of years, we're actually over 4,000 discovered exoplanets now. That's a lot. But there for a while, it was truly just a game of, let's see how many we can find in a month. It was truly just that. It was truly just, oh, look, found another one, check mark.
Research groups one-upping each other, keeping scores.
Oh, absolutely. Absolutely. It's become such a fun game. And it's not just between telescopes, it's now between countries too, because if certain countries use certain telescopes, then they're wanting to be like, oh yeah, the Italians found 10 more planets. Oh no, says the Germans. And it's just a really fun game with the exoplanetary
it's a
community.
Space race that I can get behind 100%.
It is. It's a very fun space race, to say the least. Of like who gets the telescope time and how many exoplanets can you find. But now we're realizing, can we now figure out which ones are hostile, which ones are in their habitable zones, their Goldilocks.
Right.
Yeah, and so at first it was like, okay, Goldilocks zone, habitable zone, you would need this amount of distance depending upon your host star, and therefore there's the Goldilocks zone. Turns out it's no longer that simple. It helps to know what's your host star. If you have a dinky, dim little star, you got to be real up close and personal to that star. But then if it's a big honking B-type, A-type star, you better hope to get out of there quickly, because that star's not going to last long and it's going to go poof. Or implode and explode. It's going to be fun.
You know, something messy.
Yeah, it's going to be great. So now it's just no longer distance. It's what type of star you're dealing with. Then you have something called metallicity, where how much carbon metals for astronomers is anything above helium. So you have hydrogen, helium.
That's not snobby.
Oh, it's fantastic. You can immediately know who an astronomer is. Where you're like, gee, how about this oxygen? There's metal everywhere. Great. I kid you not. That's exactly how we talk. So thinking about the metallicity, at what point of the distance from that host star would oxygen and carbon and liquid water be at a certain distance, and then you're having to deal with how does an atmosphere form? It does the size of your exoplanet, can it retain a certain atmosphere or not? I know geologists only within the past 2 years, very, very recently, have now jumped on board to the whole exoplanetary train and go, can we predict what kind of geology is on some of these exoplanets?
I was curious about that.
Yes, because if you see a certain atmosphere, that may give a good indication of, are there geysers? Are the geysers similar to what we see with Europa and Enceladus? There's no atmospheres there, but is it similar to that? Are we looking at more Neptune style, where you would have a lot of carbon, a lot of methane, but very, very large and pressurized? Or do you have something like Earth kind of deal, or volcanic?
And again, humans being very self-centered, we like to think that water, atmospheric pressure, temperatures between local freezing and local boiling are what's necessary for life. But the thing that I haven't seen is I haven't seen a lot of geologists talking to biologists yet. I imagine it's starting here at Balticon.
You heard it here, folks.
For what are the actual parameters? Where can we find limits? And the fact that we don't need sunlight and we don't need geothermal heat, as we're discovering, to drive life. Now, we might still consider the Goldilocks zone as a useful concept for complex life forms, but in terms of multicellular, in terms of significant three-dimensional architecture and so on. But for simple microbial life, I mean, we can probably eventually find a gas giant that has something resembling, microbial life somewhere in the atmosphere, is my prediction.
Yeah, that would be interesting to have almost like microbial life in like the ammonia bands of Jupiter.
Exactly.
Or something like that.
Yeah, feeding off of the sulfur dioxide, feeding off of even the primitive hydrocarbons that can be formed under extreme pressure and so on. Yeah, absolutely. So yeah, how we're using the term Goldilocks zone these days, I think it depends on what you're looking for in many cases.
Exactly.
Yeah. So is the concept, have we ruled in more planets? I think the only planets are now ruling out for possibly sustaining life are the ones that we have a definite heat signature for, like the ones that the average surface temperature is like 1,000 centigrade.
Yeah, pretty much. Now we're starting to get better with our telescopic data, where it's like, okay, are there like almost too much temperature extremes as the exoplanet would be orbiting around its host star? So now we're getting better with like the type of data that we're dealing with. The resolution of the data is starting to get better. When James Webb Telescope eventually launches, then we're gonna have like a whole new level with exoplanetary systems. And granted, it's going to give us some really pretty pictures of nebula and galaxies and black holes and whatnot. Though, but let's be honest, though, the exoplanetary community is like, James Webb, yay! Please launch at some point, please.
Get up there, work, unfold properly, deploy properly, please.
Please. Yeah. Oh goodness. We're all anxiously awaiting for that as well. We're just waiting.
I can completely imagine. Yeah.
Oh yeah.
So yeah, so I mean, as long as we've got some energy source and even radiological source, we have a 10-minute warning, that seems to work just fine. We'll probably find microbial life out there somewhere. It might be boring for many people who are hoping for bug-eyed monsters,
jellyfish,
little green aliens, but yeah, but it'll be life and it'll be non-terrestrial. I think that'll be exciting. So
Yeah, I'm still
I might be
banking
a
on
little
space
biased.
jellyfish in
I would love space
Solidus.
jellyfish. I would love
That'd
space
be great.
amoebas. So,
Oh, that'd be awesome.
what about silicon-based life at much higher temperatures? Alan Dean Foster, Prism. I remember that book. So I don't know. That's a fair question about silicon-based life at a much higher temperature. I mean, what are the limitations? I don't know silicon chemistry very well. You might
So
know it
that's
better.
actually the fun part about Venus, is that gives us a whole playground of silicates at high temperature and high pressure. So we're still very much learning about the mineralogy, the pretty rocks and everything on Venus, of what little data we actually have. But Venus, by all means, is a good starting jumping off point of what could silica based life could actually be.
Right. And I think the question there becomes, for us to consider it realistically, we would need to have some sort of functioning lab environment terrestrially where we could explore what happens. Can you build complex, not hydrocarbons, but say hydrosilicates? Can you build, polymeric silicon chains? And would that be useful as a building block? Are there a silicon-based amino acid fundamentally? Silicon-based, information storage in DNA absolutely requires carbon and nitrogen and oxygen. Could we do that with silicon and nitrogen and oxygen? Or maybe the next 5-minute warning, the next thing up, that would be what's below nitrogen on the table. I'm blanking on it right now.
Me too.
Sulfur. Would it work that way?
It's a metal.
Yeah. Hand waving. It's metallic because it's not hydrogen
It's
or helium.
metallic. It's metal.
Yeah.
It's fine.
So yeah, I think it's a matter of, can we build to consider it seriously? Can we build a lab that would let us explore that? Or can we build the tools that'll let us explore that on Venus?
Well, I could tell you right now that there are actually Venus chambers out there in the world. There's 2 that I'm aware of. One is in Ohio, one is here at Goddard, and there's one in Germany. And they are specific to high temperature, high pressure Venus type experiments. But they are for the sole purpose of looking at rocks and the mineralogy, and but
you gotta start somewhere.
yeah, but they look at how, you stick a rock in there and it changes on the atomic level. It bends the crystal structure, and they want to see, like, ooh, what kind of new rock can we create? What kind of new mineral can we create? So if anything, that it's a good starting point of, can rocks change? Answer is yes. But in what way?
Exactly. So it looks like our time is up. I'll be heading over to Homeland on the Discord. Been a long week. I'm still teaching the summer folks, by the way. So
yeah, there's your discourse right there.
Exactly. But I hope this has certainly been entertaining and engaging for many of you folks as we went to extremes in many different ways. And otherwise, lovely talking with you again, Caitlin. Pleasure.